Be starting to record. Okay, so we're recording. But we have to get to this acceptable noise range. So you have a little bit of buffer at the top and the bottom, where if you get to this point, it's an acceptable 1. If you get to this point, it's an acceptable 0. So you can really think of digital as analog, where we try to keep it in these different ranges. And so noise margin is we formally define it as the allowable voltage range on the input of a gate where the output will not be corrupted. So if we get into this intermediate range, we get outside the noise margin ranges, we lose the actual value of the circuit. And so we get in, particularly when we get into sizing and capacitances and gates, channel lengths, we have to worry about this kind of stuff. Now, we have 4 different measurements that we use to properly determine our noise regions. The first one is VIH, which, as I start describing them, they'll be intuitive. IH is input high. VIO is, so that's the minimum high input voltage. So I'm going to scroll up a little bit so you can see what I'm talking about, because this chart is a very good description of this measurement. So the minimum high input voltage means, and this is VIH here. So maybe you can see it without this going off. There we go. And then the VIH, VIL. So we have this input voltage, and we're trying to maintain a minimum high, a maximum low. That means that the minimum high means you can't go below this point on the input. The maximum low means if it goes above this point, it no longer represents the logic 0. Same thing with the output. The minimum high, VOH, and VOL is the maximum low. And NML, that stands for noise margin low, is the voltage, the input low, right? That's your maximum low input voltage minus your maximum low output. And NMH, noise margin high, is VOH minus VIH. So your input and output high. So what happens is you receive some sort of input signal. And so this is our input signals here, right? Well, that's output range. Okay, so you have your input range. I see how this works. It's going the opposite way of what I expected. Input range here, and we want to get to some sort of output range. So we have some sort of signal that's potentially degraded coming in, but we still have to reach these output ranges. So we have our noise margins, and then somehow the circuit needs to get that signal up. So we need to be able to actually create a channel using certain threshold voltages, and then based on the width and the length of the transistor, we're able to regulate that so we can destroy the signal. And so this input, when we're not able to get to the output, is known as the high noise margin, and the low noise margin is here. And so, same thing, we have our supply voltage here, our high output voltage versus our VN, so VCN. So we've got our threshold voltage. So we're trying to switch from a 1 to a 0. So we have VDD minus the absolute value of VTP minus VDD out. I'm sorry, this is VDD out. VDD minus VTP and then VDD out. So we have now established where we have our beta ratios, where the widths are correct. So it's not equal to 1 or greater than 1, because we ultimately want it to be 2. So what happens is we want it to kind of immediately get this to this point of unity gain and get out of that range quickly. So what we're trying to do here with our noise margin is, remember we have regions A, B, C, D, and E, where we start out, we're high, and then we're trying to switch to low, and it's a ratio of input to output voltage. We don't want to spend much time in here. We want to quickly get down here. Because the longer we're in here, the longer we lose information. So some people call it the indeterminate region. Some people call it the forbidden zone. Fans of Archer might call it the danger zone. Yes. Good. All right. So, but either way, you don't want to go in there. Because this is how we get ants. Or lost information. Okay, so does this make sense? Okay, so this is a simple example. We have a chart here. We have V out versus V in, sample 2.8. Question states a novel inverter has a transfer characteristic shown in figure 2.34. This is a figure from the textbook. What are the values of VIL, VIH, VOL, and VOH that give the best noise margins? What are these high and low noise margins? So, the key details is we want to stay here, and we want to be here. So high VOH, output high, 1.2 volts. VOL, voltage output low, is here. We want it to be at this line. So it's going to be 0.15. So based on this, we approximate it as 0.15. VIH is going to be 1.05, and VIL 0.3. And the reason why is it's these two. It's basically we're figuring out the points of the slope. If you remember back from algebra, you're figuring out the 2 points of the slope. Here and here, you just figure out the coordinates, and that becomes where your noise margin is, or your noise margin range is. So then to figure out NMH, you just have VOH minus VIH. So this becomes 1.2 minus 1.05. And so our noise margin range is 0.15 volts. So our noise margin is the point where our input, it ranges between 1.05 to 1.2. And likewise, our noise margin low, input voltage low, output voltage low, 0.3, which we determine here, minus 0.15, and that becomes also 0.15 volts. So in this particular simple example, we have a noise margin region based on this graph that we show 0.15 volts. I don't want to get you guys too excited. Okay, does anybody have any questions on this? All right. So that was just, I want to have that up so that way when I'm assigning homework at the end, I know what I'm doing. Okay, so in section 1, we kind of described the fundamentals of CMOS devices. We talked about the switches. We talked about the basics of the channel. Section 2, we discussed ideal and non-ideal transistor operation. So now we're going to be figuring out metrics of how we can actually make these chips actually work well, since we now know that they can be non-ideal. How do we actually take some of these designs, some of these simulations that we're going to be doing, and figuring out how to ensure that the circuit actually works, because that's what the engineering part is. So this is where you're going to start getting your hands dirty. We're going to be learning about these concepts of delay, and we're going to be learning about transient response. So we're also going to be, the reason why we're going to be learning, particularly we're going to be learning about something called RC delay, where we're going to be replacing transistors with a resistor value and then measuring capacitances in order to be able to pretty accurately determine the delay pretty quickly. And then from there, what happens is we can actually go backwards through the circuit once we determine that delay and actually determine the appropriate sizings of the circuit. We'll go through a couple of examples of that later. So we have 5 metrics for these delays. First one we're going to talk about is rising propagation delay. It's going to be from we get an input on our circuit, and then that's the amount of time it takes TPDR from input changes to arise on the output. So we have a change on our input, and then we are going to use a VDD over 2, and this time frame is our propagation delay and a rise. So that's that measure. The TGO requires the definitions, but use the graphs to make it intuitive sense. TPDF, falling propagation delay. Input changes and it causes a fall on the output. So TPDF is shown here. We have change, and then once we get from half of the input to half on the output, that is when we will actually have that's when we know our propagation rate. So when we start measuring delays in spikes, this is going to become important because you'll be able to tell how your measurements are correlating to your actual circuit. In an ideal circuit, the rise and fall times are the same. In order to make that work, you actually have to change the transistor widths to make it match, and you have to do some restoring and buffering and how body biasing impacts this. Our third metric is average propagation delay. TPD is just equal to the rising and falling propagation delay added and then divided by 2, so it's an average. And the goal is to make the average equal to both of them. The last two are rise time and fall time. These are specific to the outputs. Rise time is where you go from 0.2 of VDD to 0.8. So it's 20% to 80%. And the reason why this is important is you want to show us how quickly you're getting through your indeterminate zone. 20 to 80% is usually a good estimate of how quickly you're getting from past the noise margin through the indeterminate zone from the 0 to 1. So rise time is from 0 to 1, or in this case 0.2 times the supply voltage to 0.8 times the supply voltage. And the fall time is from 0.8 times 0.2. That's T, D, and TF. And here, that's just 0.8 to 0.2. This is a fall. And here, it's a rise from 0.2 to 0.8. And so what happens once it gets to 0.2 is it's kind of hovering here, gets really close to, but not quite 0. It's 0 for a while, and then gets to 0.2, quickly gets through, and then it's close to, but not quite, up to 1. I'm going to go past rising propagation delay here. A timing analyzer is we use timing analyzers to compute the latest time at which each node in a block of logic will switch. So we're going to be going through an example problem here in a minute where we have a number of different circuits, a number of different gates in a circuit. And based on the delay, you're going to be able to tell the longest, what's known as the critical path, which is the longest delay through the circuit. Based on that critical path, you have to make sure that all of your signals time properly. One signal, for those of you who've done advanced decisions, if a signal gets to another block before all the other signals do, it causes issues. You're doing an adder, for example, and you get the A input before you get your proper B input. Well, if you have 0, 0, and then suddenly you get a 1, you want to have 1 and 1, where you had 1 plus 0 for a while before you get 1 plus 1. So that can throw off for a certain amount of time your actual accuracy. So to measure this a little further, we're going to talk about something called slack. So we have the minimum arrival time, the required time for the circuit to operate, and the time we actually need it to get there. So positive slack means that the circuit meets the time requirement. We need it to get there in 115 nanoseconds, and it gets there early. Negative slack means that we need to get there in 115 seconds, but the circuit's taking 130 seconds, for example. I can scroll up a little bit so you can see the definitions. Does everybody have this here? So we're also going to talk about something called contamination delay, which is the minimum amount of time from when an input changes until any output starts to change the value. So that's different than rise time and fall time because we have specific portions that we need to get to, like rise and fall, we need to get to VDD over 2. Whereas this contamination delay, we have an input change, and then some amount of time occurs, and then we start getting changes on the output. So that time when you're not having anything happen, that's the contamination delay. And then 3.5, we define the critical path, as I just alluded to, as a path within the entire design with the maximum delay. And so in a carry ahead, what do you think the critical path is? So 32-bit adders instead of 1-bit adders. What do you think the critical path is? Especially for those of you who did my PhD project last semester. What's that? 15. Well, that's the number of the critical path. What's the representative value? Like what took 50 nanoseconds? What? What part of the adder? So you have A, N, and what are your inputs? What are the 3 inputs to a 1-bit adder? Input, A, and then carry. And then what are your 2 outputs? Carry out. Okay, so that means in order to start the next 1-bit adder, what do I need to do? Carry out. Yeah, you put carry out and carry in. Yeah, so your critical path is going to be your 32 carries. So that's the number you're alluding to. In the ALU they designed, the critical path was 50 nanoseconds, and what I did was I had to put buffers that held all of the inputs to make sure that they all came out at 50 nanoseconds. And this is why, because if you don't, then all your contamination delays start going off. It affects power consumption, it affects circuit accuracy, it affects all kinds of issues. So there's a type of adder when you're finishing writing that called a carry select adder that tries to address this issue by cutting the runtime from big O and big O of add over 2 by doing the first set of carries. And then what happens is they actually have 2 second adders. They have 16 1-bit adders, and then they have 32 in the second half. One of them starts with a carrying of 0, the other one starts with a carrying of 1. You get the outputs, and then you use the initial carrying from the first half to serve as a multiplexer for those 2 outputs. So it cuts the runtime in half, but you gain 3 over 2n space complexity plus the multiplexer. So that's where you're, as an engineer, you trade off. Do you want it really fast or do you want it to be cheap? So critical path is a big consideration in that. So, kind of a simple way to calculate the maximum. You start at a given node, so we're going to go through an example problem here. And then the gates to the left, you're going to use those numbers to figure out the delay before that. So here, you have to consider the longest input delay. So we have a NAND gate, and we have two inputs, right? We have a 20 and a 30 nanosecond delay. And then you have to consider, you have to add these up, and this node here is going to be 60. This isn't the solution. This is part of the problem. So there's you writing down the circuit. Just know that you're writing down the question that I've already provided on Blackboard. So as this part of this problem, you have to go through, you have to identify the critical path. You have to find the minimum amount of slack required for proper circuit operation. And part C, how would you modify the circuit to ensure both outputs of the circuit output at the exact same time? And so this is the part A is the solution. So what happens? We do the same thing. Here we go 30 and 30 is, we compare this, you see that 30 is bigger than 20. So we add 30 and 30, we get 60 at this node, which they've notated as A7. So here we have 60 and 30. We say that 60 is bigger than 20, so we're going to add 60 and 30. Here we get 90. Here we get 60 and 20. There's no other input to the inverter, so this becomes 80. This, we're going to compare the two inputs. So we have 80 and 50. 80 is bigger than 50, so 80 plus 30 becomes 110. At this node, 20 and 20 happen to be the same, so you just add 20 to 40 and you get 60. So the two inputs to this NOR gate are 90 and 60. So you compare with the two inputs. You see 90 is the biggest one. 90 and 50 becomes 140. So our two times that our outputs are 140. That's 140 and 110. So the path that takes us the whole 140 nanoseconds is this path here, because the decisions made, this is the longest one, this was the longest one over this one, this was the longest one over this input. And so if it wins every single time, that is going to be our critical path.
How did you get a 60 on the first one?
The first one here? Okay, so we start at this node, right? So we take the gate, this NAND gate, which is 30, and then we look at these initial two that are the inputs, and it's the maximum value of the input. So 30 plus 30 is 60. And so for part B, the larger value is the minimum amount of slack. So you just go 140 is the minimum amount of slack. And then for part C, the answer becomes, well, if I want these to come out at the same time, I just put a buffer that has 30 nanoseconds of slack. Then they'll both come out at 140, and they'll both work perfect. So let me scroll up a little bit so you can see the solution. So this little blurb that I have here, as you're finishing up writing the solution, is talking about any timing analyzer has to consider rising delays, falling delays, rise times, fall times, slack, input capacitances, output capacitances, and all of that has to be done in order to ensure that you have a properly working circuit. So we're going to be going over some examples of how you can kind of use some methods to try to use the last problem we're doing in this section is actually going to be, we have a 6-input AND gate. And we have 4 different ways we design it. One, we have a 6-input NAND gate we invert. One of them, we have a series of, we have 2 3-input NAND gates and a NOR gate. And one of them actually has 4 stages. And we're going to figure out which times we want to use which design. And it's going to be based on the output capacitance that we need. Because the output capacitance is going to be driven by what's known as fan out. Fan out is the number of circuits that are driving based on one node. So you're going to see that one of the circuits works really well if you have low fan out, but another one entirely works when you start having high fan out. And high fan out is what happens if you're trying to control losses. So for example, a 6-input AND gate is a very good example because MIPS in the single cycle data path uses 6-input AND gates for their control signals. The control signals have to be able to decide what's happening in the ALU, what's happening in the registers, what's happening in the data memory. So if you want to design it to the CMOS level, you want to use these a different type of 6-input AND gate in order to be able to drive the circuit properly. So that's the general idea of this blurb. So a more formalized description of what happens when the output changes versus the input changes is what's known as transient analysis. So up to this point, we've kind of just considered a 0 happens and then a 1 happens, and we're starting to realize that we don't quite have it accurate all the time. So transient analysis is defined as a measurement of the impact on the output voltage over unit time. So this is a function V out of t if Vn of t changes. So we have some t, some event occurs, and then we have some sort of change on the output. The measurement of that is in this transient analysis. And the programming language is very good for transient analysis. It's known as SPICE. So SPICE stands for Simulated Programming for Integrated Circuit Synthesis. So when we start getting into section 5 is going to be just a big dive into SPICE. So the first 4 sections are kind of figuring out what it is we need to do in order to be able to be good VLSI, CMOS design engineers, and then the rest of it's figuring out how to apply all of that using tools to build bigger circuits. So here we have an inverter with a step function input, and we have a PMOS and an NMOS, and we have our supply drain source current going through our NMOS transistor. To recall, our current is dependent upon capacitance and the rate of change of voltage over time. In the previous session, we used this relationship to prove a lot of our beta ratios and what the voltages contribute to our drain source current at any given moment in the linear cutoff and saturation. We're going to apply what we know here to figuring out the direct relationship between the drain source current and the rate of change of voltage. So again, in cutoff is cutoff. We don't want any current. So it's 0. So VDS is actually becomes V out of T because that becomes our output voltage versus our input voltage here. And then same thing, saturation made over 2 supply voltage minus threshold. So once you reach saturation, that input voltage, if you're still in that saturation region, or we get pinched off, that's what's going to happen here. This should be greater than. Anyway, that's TGO, so I can just fix that later. So I have what's the first graphic of the sign is a 5-minute video about. It's a real brief description, something very similar to what's known as a source follower circuit. So the whole idea of this is we need to start being able to estimate delay. So we want to be able to make it easy. It's not as accurate as simulation, but having a simulation requires writing code, and writing code can take a lot of time. And also, the effectiveness of the problems that we're going to be doing in this section. So the big mistake, and the big mistake that people made in CMOS back at USF in the lab, is they would just write code, and they would write up some circuit, and it wouldn't quite work, and then they'd tinker with their code, and 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 then next thing you know, they've been there for 3 days and they want to rip their hair out. The proper way to address this is to actually start working on these problems to determine these ratios in the way the circuit should operate. For example, the effective resistance is the ratio of the drain source voltage the IDS averages across the desired switching interval. We start figuring that out by determining gate capacitances. Sorry, okay, we'll see that. So you need to find the proper way to design the diffusion areas in certain circuits. So we're going to be going over an example of two proper designs of state diagrams of a two-input AND gate. And we're going to see, based on these diffusion capacitances, which one is better. And so the way of doing this is we're going to be going over what's known as an RC model. So up to this point, we had PMOS and NMOS transistors, right? And we inherently know that there's some sort of resistance and there's some sort of capacitance. So now we're going to go over the formal model where we're going to convert the PMOS and NMOS transistors into RC circuits. And based on that RC circuit, the amount of capacitance and the amount of resistance at the input and the output is going to directly correlate very, very, very closely. And we'll see the diagram, which is slightly different to the actual delay of the circuit. And so before you go in and before you dig into your designs, this is a good thing to do. This is what I did to save me a lot of time. And when I took, actually I still hold this design, the record for the smallest design in that class.
That's not a surprise.
I'm not bragging, I'm just smarter, not harder. Would you rather spend 3 weeks in a lab or would you rather get in and get out? That's the military training advantage, so my smarter or just more prepared. Okay, so this TGO 3.8, this is our actual converted. So this is an NMOS transistor. And so we have an instance of resistor, an input capacitance. Now this value K, this is where it becomes important because this is where it has the width. So when we start scaling in 3-input AND gates, 3-input NOR gates, this value K is going to relate to the number of transistors we have in series. So, for example, to preview, let's say we have a 2-input NAND gate, right? So here's our PMOS, here's our PMOS, we have our inputs, and we have here. Well, we want it to relate to the effective resistance of an inverter as much as possible. Well, what's going to happen is when they're in parallel, it's going to stay the same. And the reason why is if we don't keep it the same, we start adding capacitance. But if we put in series, we need to start actually accounting for each one. So if it's an inverter, it's going to be 2 and 1. So if it's an inverter, it's going to be 2 and then 1 for our K value. But we do this and start adding 2 here to the width. Now, if we did a 2-input NOR, I mean 1 is going to stay 1 because they're in parallel, and then you start having to multiply by 2. So now instead of 2 and 2, it's going to be 4 and 4. And so you can see here, the PMOS version, 2R over K, this is the resistance is going to go down, but the capacitance doubles. So what you're going to see is you're going to see that it becomes much more advantageous to use NAND gates instead of NOR gates. Because you can see a 3-input NAND gate versus a 3-input NOR gate, you start adding capacitance much faster. Just multiply it by 2 instead of multiply by 4. And so you have a input capacitance KC, you have an output capacitance here, it ties to ground. This is source and drain. What we're going to see in pull-up and pull-down networks is how we can separate these to ensure that this capacitance ties to the output and this capacitance ties to the input. And then we're going to see how they're additive, and then we can maybe use these techniques to try to minimize the circuit capacitance. Additionally, for PMOS, we have our source and drain. We have a capacitance KC, so it's initially going to be 2, right? So it's 2 here, so that's going to cancel out, and we're going to see how the resistance is going to maintain the same resistance throughout the inverter. So we want to cut in half. So if the resistance for both the PMOS and the NMOS is the same, that's when your beta ratios are going to be the same, and that's when you're having proper circuit operation. Here, source in a pull-up network, a lot of they're going to be ideally tied to VDD. However, in this case, it's not, and you're going to see how that works. This KC here is tied to supply voltage VDD, as is this one. And this gate switch represents where the CMOS transistor was. And so I kind of have a brief little kind of rule of thumb. This would be good for you when you do your exam. You kind of refer to this TGO as you're working through it. The first one, for each PMOS pass, set K equal to 2 times the number of PMOS transistors the current must flow through. So 2 NOR gate, 2 times 2 is 4. Same thing with NMOS. Set K, 1 times the number of transistors. So here, 1 times 2 is 2 for your NAND gate. Substitute transistors with their equivalent RC circuits. And then determine which capacitances contribute when the output is switching. And I'll show you how to do that in the example problem coming up. Those, remember from your circuits classes back in the day, resistors add in series, capacitors add in parallel. And if you remember, in parallel, 1 over R total is equal to 1 over R1 plus 1 over R2 plus dot 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 plus 1 over Rn is equal to the summation I equals 1 to N 1 over R of I. And if you're adding capacitors in series, just replace everything in this little equation here with C. And that's how it's done. And you're going to compute the input capacitance for each input by adding the non-switching capacitances. So to scroll up here, if we're putting these together, what's going to happen is you see how this capacitor is affected by the switching, and this one doesn't seem to be because it's tied to the supply voltage no matter what. You'll see how that contributes. I'm sorry, this is the NMOS. This is the one that contributes to the switching because you have a switch, and this one can dissipate or charge. This one's tied to ground no matter what, so it is a non-switching. Again, here non-switching versus switching because you have the output pertaining to the switch. And then we're going to compute the output capacitance for all capacitors at the output node. So this is just they're typically going to be in parallel, which is good because they'll add up. Okay, so I'm going to go past the first 3 stages here. So past substitute transistors with their equivalent RC circuits. Okay, so this is a fundamental example, 3.2. Draw the RC delay model for a CMOS inverter and determine the RC delay. So here we start out. going by steps, we only have to go through one PMOS or one NMOS converter. So it's 2 times 1 and 1 times 1. So K for the PMOS is going to be equal to 2. K for the NMOS is going to be equal to 1. And so what's going to happen is you take those transistors and you put them here. So here we've switched it out. We switched the PMOS out here. We have this capacitor here that contributes to the output, as you can see. And then this here is a non-switching above the resistor. And this becomes 2R over K, which becomes 2R over 2, which becomes R, just like we hoped. Grow up just a little more. For the NMOS, we have the same. We have substituted this circuit here for the NMOS. You see how it's out in parallel once you can actually see on the screen here. Come on. There you go. We have the equivalent capacitances below. As you can see, we have the capacitance below. We have the capacitance. This capacitor here is the same as this capacitor when the switch is on. And then we have another capacitor on the output. So then what happens is we're going to actually start combining these. So we have the non-switching output capacitance and this non-switching here. We don't worry about those. We worry about these two. So these are all in parallel. So 2, 4, 5, 6. And then our resistors add up. With our resistor here, so when the output is going to be one or the other, turning on or off, this on the switch. So this simplifies down to a simple RC circuit. We have a resistor and 6 capacitors. And so 6 RC, this is a classic solution for the delay, for the RC simulation delay of an inverter. So this is kind of a fundamental proof of something that is widely known. Yes?
How did you determine the K?
K is determined by, for PMOS, it's 2 times the number of circuits go through the path. For NMOS, it's 1 times the number of circuits go through the path. So K for PMOS is going to be 2 times 1, because we're only going through 1 PMOS. K times 1, here's 1 times 1, because we're only going through 1 NMOS. From there, there's applied to the pull-down network. I should be clear about K. This K applies to the pull-up network for PMOS. And from there, it just becomes additive based on the switch. And here, the reason why this is done here is because, and we're going to see examples, particularly for NAND gates, where we're going to be dealing with best case and worst case switching. So for 3.1 NAND gate, you have an instance where you have 1, 1, 1, right? And that's the only instance where you have a 0 on the output. So what happens if you switch one of the inputs? Then you start having to worry about, well, now we have to go up to the pull-up network. Then you have to deal with the max. 2 of them are still going to be on because 2 of the NMOS transistors are going to still be on, but 1 of the PMOS transistors has to be switched. And because that PMOS is switched, that's when it's going to contribute. Since that's the worst case scenario, that capacitance is going to be higher, and that's when we deal with that switch. So here, either one resistor or the other is switched on. Since 2R over 2 happens to be the same as R over 1, that makes it easy to calculate. And if you allow me, I'll come back up so you can finish copying. But when we get past this, we're going to start seeing how this tau is equal to RC in this RC circuit, and you're actually going to see how this tau directly relates to the amount of time it takes to have a falling propagation delay. So this does end up having a direct correlation. And so I did indicate here, especially if you're looking back on it, I did write non-switching tied to ground and not output. See how it's tied to ground here? That is why when we go over to this part where we start doing the additive RC circuit, that this capacitor didn't count. Likewise up here, so you switch it off, the R goes away and this 2C goes away. We switch it on, what's always tied to ground, so it's going to come through here. But this is known as input capacitance. So we're going to deal with that a little later. These non-switching tie into the input capacitance. So we're going to have a situation where we say we have a 3-input NAND gate that is driving H number of outputs of identical NAND gate circuits. We'll be able to figure that out specifically. Now the input capacitance is 2C. These are in parallel. So the input capacitance of the inverter is going to be 3C. And then we're going to be dealing with all the circuits are going to have the ratio with respect to the input capacitance. So we're going to determine that the input capacitance for a 2-input NAND gate is 4. So we're going to use 4 over 3 as the ratio to help calculate, because everything was going to relate to the inverter calculations. Does anybody have any other questions on 3.2? Yes, Coleman.
Where you in the end you get 6C. So the two 2Cs are in parallel. In the picture, of course, the two 2Cs are in parallel, and then the two rated Cs are in parallel. How do you? Wouldn't those then be in series with each other? Or do you consider
they're all the same number? So this would be. Looks like that. That's a good question. This is an important point. This is all the same node right here. Does that make sense, everyone?
I was confused. One's tied to ground, the other's tied to VDD.
Yeah, but this is all the same. Yeah. They're all going into the same time. This is the output. So it's with respect to the unit from the other. So this is where it starts getting a little more complicated. So we have a 3-input NAND gate here. And we're going to be doing the same thing. So let me scroll all the way down here to show you what I'm talking about. So the question reads, draw the RC delay model for a 3-input NAND gate. Sketch the equivalent circuits for the worst case output transition for rising and falling. So this is a new aspect of it. So I'm going to zoom in here a little further so you guys can see if it actually lets me. I'll go in even further. All right, so we have our conventional 3-input NAND gate. So we start with the K ratios. For NAND gate, you only have to go through one CMOS to get to the output. So it's going to be K equals 2 times 1, right? So here we can find our K for PMOS is 2 times 1. For NMOS, it has to go through all 3 NMOS transistors, right? To get from ground to the output. So to do the proper RC delay model, we have to find K equals 1 times 3. So if you remember back to the stick diagram, the reason why is now you're going from VDD, you're going up to the end diffusion region, and you're going through all 3 polars. Now we have all these capacitances, these shared and merged and intrusive diffusion capacitances. So now you're dealing with all of that. So now we're multiplying it times 3. So the next step is going to be this step, and then I'll show you how I get down here in a second. So replacing all of these, I've shown you which ones are switching and which ones are not switching. So here, this is ties from the input to VDD. Again, here, this is a switching one because you can see this one here, and this one here apply to the output. So it's going to become 2, 4, and 6. And then the only capacitor from the NMOS that's going to be on the output is this one here. So your output capacitance is going to be 9C.
What about the capacitor on the far left is obviously not connected, but what about that one and the other two?
This one?
One more.
This one?
Yes.
Because it's driving the input. Side of VDD and it's driving the input. It is here. This is the distinction. So the capacitor is a plate between two charges, right?
Yes.
Charge 1 is here on VDD. Charge 2 is on the input. It is not driving the output. Driving the output means you have some sort of change on the difference of the capacitor will change directly to the output. Right? Another way of drawing it is people will actually draw like this. We'll draw capacitor like that.
Sorry, it's just confusing.
Okay. And I messed up one of its plates is directly tied to the output. No, it is not. I'm telling you, it's not. Is this tied to? Does it go through anything before it gets to output? Yep.
All right. So if it goes through anything.
Yes. Here, the plate, the other plate is tied directly. It's a knockout. Okay. So then what you're going to see is you're going to start adding some of these together, right? So this is where these guys come in. So you have your input tied to, if you drew each one of them like this and got rid of that'd be just as accurate as it's driving this one. And it's also driving, here, this input is driving the NMOS. This input is driving the NMOS. And this input is driving the NMOS. So when they're in parallel, what this means is this could be A and this could be A, right? So what's going to happen is they're going to start adding together, because this input node is the same as this input node, right? So this is going to tie together, and then you're going to, since they're going to be in parallel, coming in the same node, that's when you're going to have your input capacitance here. As you can see down here at the bottom, that's 5C. That's 3 plus 2. So that's why it's not switching, because it's directly. That's bothering me. But this is definitely in the same input. Like that is not contributed to the output. Like 9C and 5C are right. I'd bet my life on it. Right. So here, what we're going to end up doing is when we calculate the worst case scenario, we're going to be taking the resistors it goes through. Once we calculate this, what's known as an Elmore delay here in a minute, we go through the resistor 1, we go positive capacitance, and the second one is going to go through second resistor times this capacitance, and it's going to be third resistor times the output capacitance. But for the falling, Remember, it's R divided by K, right? For the NMOS transistors. So what's going to happen is, this is what's known as the worst case scenario, precisely because in order to go through, it must go through all three transistors. So we have 3 resistors here. We have our 9 C's, our final output guided capacitance, is driven by everything tied to that node on the output. And additionally, we have these 2 additional capacitors, which represent the 2 internal capacitances of these transistors.
Can you give that up to that?
Yeah, sure. I'm going to zoom out a little here. This one right here? Okay.
Where did you exactly get a 9C and 5C?
9C is, to go over here, 2 plus 2 plus 2 is 6, plus 3 is 9.
Oh.
And so the way you want to draw that out, if you're drawing it out, working through it, you have this transistor for PMOS, right? And then you have your capacitor times the supply voltage. And then you have another capacitor here, which goes to supply voltage, but it's on the node. Same thing, you're going to have a second one. Capacitor here. It's all on the same node. We tie these together, so this node is here, this node is the same. And so this is 2C, 2C, this is 2C, this is 2C. And then third, we have another capacitor. 2C, this goes to the supply, and this also is here, 2C. Now, the reason why these 3 are together, this one, and this one, is because they're all the same node. And this is output. So this is 2C plus 2C plus 2C, and then we start adding here, right? So this is going to have a 3C, which goes to ground. This ties to the same node, so now we add 6C plus 3C is going to be 9C. So to take it a step further, we have these input capacitances for the NMOS transistors. They only add with the input that ties in for that specific input. And so that's 3 plus 2 becomes 5. And so what's going to happen is we're going to have an example where we have a 3-input NAND gate, which is going to drive the fan out, known as some n number of 3-input NAND gates, right? So then what's the capacitance there? We're going to learn that it's 9 plus 5H C, because H is the number of circuits it's driving. So the output capacitance here is 9, but it's only driving one specific input. So that's where it's driving one specific input on all of the gates. So that becomes H, number of gates. But one input, so that's 9 plus 5 HC. Trust the quantity. Now to go to the worst case scenario, so this was the worst case scenario for NMOS because it has to go through all 3. Anything to 1, 1, 1, it must go through all the NMOS as I've indicated here. So for PMOS, we have a situation where we go from 1, 1, 1 to 1, 1, 0. One of our inputs is switched. So we still have 2 transistors going, right? For the NMOS. But we have 1 for PMOS. Now the reason why this is R over 3, recall R over K is the resistance of the NMOS transistors. And 2R over K is the resistance of the PMOS transistor. So here, K was 2 for PMOS because we only have to go through 1. But you still have to go R3 for these resistances here. So this is the worst case scenario. We have 1 output driven. So we have 9, we have additional 3C, and additional 3C here, driving these 2 particular NMOS circuits. So I'm going to zoom out just a little further. So this is the worst case circuit. For switching, for rising, because it's going to go from 0 to 1. These are all 1s except one case where it's 0. And for worst case for falling, is when all 3 NMOS resistors have to be activated. Does this make sense? Okay. Yeah. I actually went and reviewed it this morning. No, I mean, the key thing to remember is all of this is a good tool to use as you're designing the circuit. It's going to be a very close approximation to the actual. Okay. We'll stop here. Sure. I'm going to. So before I do that, the homework assignment is.
You get 228, so we started right.
Yeah, 228. 39 TGOs. And then examples 3.1 through 3.3. And then the example for, I think we only had one, 2.8. Sorry, I'll let you copy it down again in a second. And that's 2.8 and it goes through 2.29. So this is the homework assignment. Okay, does anybody have any questions before I dismiss you? Okay. I'll leave this up as long as you need. I'm also zoom out to 100 so that way you can see the entire problem as you're copying it down. But I'm going to stop the recording